Here we're going to look at one of the fundamental rules when it comes to differentiation, a rule called the chain rule. Now this is something we've touched on in previous years, but we need to make sure that we're 100% up on the technique, we know where it comes from and we know how to utilise it. Now basically what this means is that if we have some function g of x, which is differentiable at a value x, so we can calculate the derivative at that point, and we have another function f, which is differentiable at that exact same point given by g of x, then if we take the two of them and make a composite function f of g of x, this is also differentiable at that point. So if we can calculate the derivative of the inner function, derivative of the outer function, when we combine the two of them and make a composite function, we can calculate the derivative of that whole composite function. That means that we can essentially say that y dashed of x equals f dashed of g of x times g dashed of x. This here, this is what's called the chain rule. So this is how we take the derivative of two functions like that, which are within one another. Now, it seems fairly complex when we're thinking of it like that, but try to remember it's essentially differentiating the overall function, then multiplying it by the derivative of what's within it. Yeah, the notation can sometimes get people a little bit riled up, but that's essentially all it's going on about. Now what we have to do is we have to be able to think to ourselves, how does this work? How do I know it works and how could I prove it? Well, let's work that through and see what we can do. Now let's imagine I've got some function y equals f of g of x. So just as we want before. And I want to find the derivative of that. What I'm going to do is I'm going to set u equal to g of x itself. So I can slightly change my notation for y based on that. Just make it slightly easier and neater using that substitution. What I'm also going to do is set a value t to be given by g of x plus h, take away g of x. So it's going to be the difference between two parts of the function, g of x and g of x plus h. So it's going to be given by that. What we know is if we use the formula that we know for the derivative, we know that y dashed is going to be given by the limit as h tends towards 0 of f of g of x plus h, so f of g of x plus h, because it's the derivative at the next value, take away f of g of x, all divided by h. So that there is the formula based on the formula of my derivative. Now, I know that g of x is equal to u based on what I've said originally, so if I substitute that into here, this will actually make my life a heck of a lot easier, because this first part, what I'll then be able to do is say limit as h tends towards 0 can be given by f. Now I want to write this in terms of u or t, some other way of writing it. If I take this here, t equals g of x plus h, take away g of x, I can rewrite it to get rid of this as g of x plus h equals g of x plus t. Now we know g of x is u, so that's going to equal u plus t. Again, u is whatever we would substitute into these functions. So what I'm then able to do is use this to rewrite my derivative formula, and I can rewrite it as f of, well, g of x plus h here is given by this here, so f of u plus t, take away what would be f of g of x, but I know u is equal to g of x, take away f of u, all divided by, well, I'm looking for h for the bottom there. Now what I want to do is look at this and think, right, how can I relate the variables to each other? Ideally what I want to do is get rid of the h, because the t in this would represent the change. Now remember, calculating the derivative is the difference between two consecutive parts of the function. Now the two consecutive parts of the function here are the u plus t and the u. So ideally on the bottom, I don't want h, I want t. So what we have to do is change that, and we have to write the limit as h tends towards 0 of f of u plus t, take away f of u, all over t. Now, the issue is that h and t are not equal. So in order to get t at the bottom, what I'm going to do is take h out as the derivative of another fraction, where I'm going to make the numerator equal to t. Because if I then simplify it, the t up here and the t in the numerator of my new fraction, which is going to be t over h, would cancel, and I'd get back to what I had before. Now, I'm going to split this off into two different functions, and what I'm going to say is fine. So the limit as h tends towards 0 of the first part, f of u plus t, take away f of u, all over t. That's going to be then times the second part, the limit as h tends towards 0 of t over h. So now that I've got that, I have to then split it all up. Well, before I do that, what I can do is remember that for t, I can go back to this bit here and look at this first section before I've modified it and remind myself that t is equal to g of x plus h, take away g of x. So I can rewrite it yet again as the limit as h tends towards 0 of this first one, f of u plus t, take away f of u, all over t, and then substitute in for t in this one, times the limit as h tends towards 0 of t, which I'm now going to rewrite as g of x plus h, take away g of x, so g of x plus h, take away g of x, all over h. So I've now rewritten it in that format there. Now, one thing you need to look at and note in this case is because of the way these match up, as h tends towards 0, t will tend towards 0 as well. So what I can do is, because of this, I can look at this first one here and say the limit as h tends towards 0 will be the equivalent of the limit as t tends towards 0. It's the same logic as we would use previously when calculating the derivative. It's the difference between two consecutive parts. The only difference is in this one, u plus t take away f of u. This time, the t is the difference between them. So that's what we base it on, t tending towards 0. That's why, as h tends towards 0, t tends towards 0 as well. From that, what I'm then able to say is I've got f dashed of u times g dashed of x. Because it's the derivative here, the only difference is instead of x, I've got it written in terms of some other variable u. But if I go right back to the start, I know u is this function g of x. So that then means that's the equivalent of f dashed of g of x times g dashed of x. So there you go. That there is proof of where that rule comes from. That's where there is proof of where the chain rule comes from. Now, when we're doing it in terms of Leibniz notation, it's the same idea. We just rewrite it ever so slightly. So if we have y equals f of g of x, for our consecutive normal notation, we can then rewrite it as dy by dx equals dy by du times du by dx. And what we would do in this case, we'd set u equal to g of x, calculate derivatives for both, and then substitute back in at the end. So there you go, proof of the chain rule. What we have to do is be able to use it, so I'm going to show you a couple of examples of this now. So let's imagine I want to find the derivative of 2x minus 3 to the power of 5. So for 2x minus 3, first thing we do is we identify the overall function f and then the inner function g, because remember we want f of g of x. Now, as we get more and more used to this, it'll become more straightforward to be able to do it, and we should be able to do it instantly. But looking at this sort of question here, the g of x, in this case, would be the 2x minus 3. That's because that is having the overall effect of the f of x done to it, because the f of x is this outer part here, so the f of x would be whatever the function is to the power of 5. In this case, though, we've just got more than simply an x. So what we have to do is take the derivative of this and then times it by the derivative of this. So for that, I'd bring down the 5, a 5 bracket 2x minus 3 to the power of 4, and then multiply it by the derivative in here, which is just 2. So from that, I can then say dy by dx is equal to 10 bracket 2x minus 3 to the power of 4. So there you go. Simple application of the chain rule and how we would work it through when it comes to a question. Now this is the same regardless of what the outer function in terms of f is. It could involve trigonometric functions, exponential, logarithmic functions. It doesn't matter as long as we can represent it in the format f of g of x and we can work it through. Now sometimes using a substitution helps us, as I'm going to show you just now. Let's imagine I ask you to differentiate sine of x squared plus 3x. Now this is a slightly more complex looking function than we'd be used to. So let's imagine I want to take my f of g of x, which is going to be this, and rewrite it as f of u. For me to do that, I'd have to say that u equals x squared plus 3x. Now remember, if I've got f of u, what I've got is f dashed of u times the derivative of u. So let's say u dashed. That there is going to be my overall derivative. So I'm then able to say is that f dashed of g of x, that's equal to, well, f dashed of u. So in this case, f of u is equal to sine of u. So derivative of sine of u is equal to cos u. It's then going to be times whatever the u is, the derivative of that. So u dashed is given by the derivative of x squared plus 3x. So it's given by 2x plus 3. Now, at this point, we've got a u in there. Let's substitute in, get rid of that, and put the whole thing back in terms of x. So to do that, I'd keep my 2x plus 3 on the outside, and I'd then multiply it by this part of the derivative here, but I'd substitute in for u, so it would be 2x plus 3 times cos, and instead of u, it would be cos of x squared plus 3x. So there you go, I've got my derivative using that rule. Using a chain rule, it's something that we need to be able to work with and we need to be able to do quite effectively and efficiently, particularly with more complex functions, so that we're able to calculate an answer for those.